stay in the fucking saddle. You don't get flown.
All right, welcome back, everybody. As folks are filtering back in, I'm going to announce a couple more of the raffle winners. So here I've still got Stephanie, this raffle winner for item number 2. Next couple of items, we've got a baseball cap that's been donated by the Kings. We've got I guess it would be a toque on the other side of the St. Lawrence River, but a little winter beanie hat from the Flyers, and another Hockey Fights Cancer winner toque from the Devils. So a couple more winners here. So next winner is Jeff Greenstein from good old New York, New York. So congratulations to Jeff. Winner from Calgary, so awesome. Right, see Western Canada represented here among our winners. So Tim Gency, winner of the 4th raffle. And our 5th raffle from Ottawa, Ontario. So nice to see those. And again, thanks to our sponsors, particularly the teams that generated or that donated those items to make this possible. So we're going to move into the next session. And so our next speaker is Connor Jung. And it is particularly my pleasure because many years ago, Connor was my mentee as part of the Hockey Graphs mentoring program. So Connor currently works for 2K, dealing primarily in fraud and cheat detection. He was previously a data analyst at SportLogic, working on expected goals and team reports and building metrics from event and tracking data. He now runs apple-hockey.com. So it's a comprehensive prospects analytics website that is currently free to the public. I don't like the tone of that. It's going to keep being free, right, Connor? Yeah. I will turn it over to Connor. And yeah, I can see your screen. We're all set. Hold on one second, Connor. I need to remind everybody that we are recording all of these. And that if you have questions, put them in the Q&A, and we've got folks monitoring those, and I will pass those to Connor at the end of his talk. Go ahead, Connor.
Awesome. Michael, I think you left out the fact that I was probably the worst mentee of all time when it comes to the hockey mentorship program. We had a couple of email exchanges. You had followed up, but I had kind of gone and ghosted you because I was kind of overwhelmed with my first job after graduating. But all the well, we're here now. First off, just want to thank the organizers, Dr. Shuckers, Louisa, Megan, for putting on a conference that's super accessible and free for the public. You guys are doing God's work. I also want to congratulate, anyone who was actually able to submit for the Big Data Cup. I've worked firsthand with this type of data spec. It's not an easy data set to work with. So sometimes you feel like you're, spending more time actually looking at the data than actually doing the analysis. So stick taps to everyone. You guys are joining me today to talk about prospects. I tried to cram as many, machine learning and data science buzzwords into one title. I know this isn't Sloan, but you guys are gonna have to bear with me. So this is kind of the agenda for today. We're gonna do some brief introductions. We're gonna do a literature review. We're gonna do a slight model framework. We'll look at the comparisons for the model. We'll do a retrospective. We'll take a look at some draft value. We'll look ahead to the 2021 draft. We'll talk about the website, and then we'll have time for questions at the end. So my name is Connor, and as Michael said, I currently work at 2K. Most of you probably know me from my time at SportLogic, where I was a data analyst, and now I run a website called apple-hockey.com, where this model resides. I've also added some links to some previous research that I've done. I'm sure these slides will go out at the end of the conference, and so you guys can all click around and follow through afterwards. So where are we right now when it comes to prospect analytics? The roadmap that got us here is quite extensive. It's quite large. This by no means is an exhaustive list. Just those that I've leveraged for this research. I just want to shout out to metahockey.com. It's an amazing resource for looking at past research. And it's also, prospect analytics as well as the NHL draft is kind of the most research topic. It feels like if you go to metahockey.com, and it's easy to see why. Prospect development, the draft, it's kind of the backbone of building a strong NHL team with the draft, prospect development, and asset management and the likes. For me,
Connor,
there's kind of three.
Sorry, I need to interrupt you.
Yeah.
Yeah, I don't think we're seeing your slides as they forward through. We're still on the first slide. Okay, there we go.
Oh my goodness.
Yep, now we're seeing all of that, so we're good.
Okay.
Sorry.
Sounds good. Sorry about that. So yeah, this is the roadmap that I was talking about. It's kind of a non-exhaustive list of sources that I kind of drew for this project. For me, there's kind of three kind of main pillars when it comes to prospect analytics. There's people who've done work in league translations, adjusted scoring, and draft value. This project kind of draws on all three of these. So what's the problem that we're trying to tackle? In my opinion, there's really kind of one major, I wouldn't say major, but a shortcoming and limitation when it comes to prospect analytics, and that's the response variable. To me, whether it's 200 games played threshold or points per game or point share the last 7 years after a player was drafted. To me, I think we can be a little bit more fine. And so the idea is that we're going to fit on a less coarse response variable, and that's just future performance. Because the idea and the thesis is if we can better approximate intermediate steps of player development, then we should be able to better approximate a player's NHL potential. So data and assumptions. We're using elite prospects data. I know there's probably someone on this call at a recent OTTHAC who told me that elite prospects data is an inch wide but a mile deep, whereas the data spec at Stathletes or any other event data set is a mile wide and an inch deep. So we're going to be using this because we want to feed the model as much data as possible. And some assumptions that we're going to have is we're going to look at a player's league. We're going to try to project a player's league based on their performance in this current year. Their performance in that next year is then dependent on that league, and that league is known, and so that their scoring is kind of a weighted function of past performance. Another thing to note is that, in my opinion, age is kind of has a non-linear impact on scoring. So I don't do any age adjustment scoring as done by something like PCS. I do error adjusted scoring though. And then the last is that NHL teams draft relatively efficiently in the long run, which is why I'm adding something like draft pedigree as one of the features in the model. So in terms of the model architecture, there's really two main components. There's a league prediction model and there's a scoring prediction model. The first we can kind of see is the league prediction model in this slide, which is, take, for example, Mark Stone, who was drafted by Ottawa in 2010. What we're trying to do is we're just trying to predict what that player is going to, what league that player is going to play in that next year. So we're going to take features like their points per game, height, weight, whether they were drafted in that season or not, and a myriad of other factors to try to project whether that player is going to play, whether it's the WHL, the AHL, the NHL in that subsequent season. This is a pretty simple model. You can use it's a multi-class classification problem, so you can use anything from linear regression to XGBoost. I chose XGBoost, for example. And so you can kind of see how these components kind of create somewhat of a sequential pipeline in a way, where you start with these player seasons, you have this player vector, you predict that subsequent season, and then that subsequent season, you try to predict their performance. That loop basically comes back again. You do this until that player essentially ages out. So take, for example, Jake Sanderson, who was an Ottawa Senators first rounder this past year, who just completed his campaign at Notre Dame, I believe. We're basically just trying to fill out these negative ones with predictions. So how are we going to do that? We talked about how we wanted to have past performance predict future performance. What we're going to use is a recurrent neural network framework called an LSTM. Stands for long-short-term memory. It's a fancy way of saying it's just a training loop for a bunch of cells that are kind of chained together. These chained cells are essentially just like a conveyor belt of information, and there are these linear and nonlinear functions inside these cells that control the flow of information. And the model basically learns how much information flows through. The thing that makes LSTMs special are these hidden states. And like I said before, we have these, it's basically like the memory of the model. And so as we said before, we want past performance to help predict future performance. And so what's the analog to hockey? Well, take our Mark Stone example again, where our XT matrix is basically just the player feature vector, where you have their position, games played in that next year, that league, and then their performance from the previous year. And we're basically just trying to predict their performance in the following year. So if you think about it, it's almost like in economics, where it's almost just like forecast projections, which an LSTM is well suited for. This was really my first time using neural networks, and from people who have used R or Python and are accustomed to using things like model.fit and just and just being as easy as that, training neural networks is not that. You have to do things like pad sequences. So from before, when you saw Jake Sanderson, you saw a bunch of these -1s. You basically want to feed the model a very structured tensor. So at least for this, I chose 7 seasons. So you want to basically feed it the same dimensions each time for it to generalize well. There's some hyperparameter tuning that you have to do, and then there's some training conditions that you have to set. And basically, you just end up waiting. And for me, when I first did this project, it was at the height of the pandemic, so I was left really with nothing to do, with my computer basically being maxed out. And I basically took that time to take up golf and lowered my handicap by about 10 strokes. So what are the model evaluation metrics? So for me, I'm using a baseline of trusty old XGBoost. For me, it's kind of an easy model to go to get something really performant and optimized to try to beat, essentially. If you can beat XGBoost, then you're doing a pretty good job. And at the first pass, LSTM doesn't do that. XGBoost does a really, really good job of fitting on the training data, but LSTM also does a decent job as well. With a 0.7 R squared for the training, for their training sets, it kind of falls off a bit when it comes to out of sample results. And both models do tend to overfit, and this is kind of the capped out XGBoost model as well. I did a little bit of bootstrapping with XGBoost, but it still seemed to overfit the training data quite heavily. But if we kind of look at the distribution of the predictions of future performance, it looks like the LSTM actually does pretty well of actually fitting the ground truth, whereas the XGBoost model, it seems to be, biased in terms of the mean. And so that kind of gave me pros to kind of move on and see if we can tailor solution for overfitting. So there's a lot of things that we can do for overfitting on a machine learning model, specifically neural nets. There's regularization, early stopping, tuning of the hyperparameters, as well as sampling. And what I chose was a combination of having a penalization term. I chose 1/10 of the number of training periods, increase the learning rate, and decrease the number of LSTM layers. Wrap that all around 100 different models using bootstrap resampling, and the results were actually really good. We were actually able to match the out of sample results to match the training results, essentially. 0.7 R squared for the 100 bootstrapped LSTM, and a mean squared error that edges out XGBoost, the maxed out XGBoost, that is. So this was an interesting finding. I wasn't expecting the model to perform this well, but I'm happy that we were able to get something out of it. So essentially now we can actually simulate player development. We've actually got all of the components that we need to essentially project the players that we don't know. So for example, take the Jake Sanderson example. We'll predict his leagues, the possible leagues that he can play in that draft +1 season. We loop over those leagues and predict scoring for all of those leagues. We append those predictions to the original player data set. We'll increment that league, or that year that is, and we'll repeat this process until we exit out. The exit condition, like we said, is that draft +5 season. So that, and age is part of the model, so it doesn't really matter if that player was a 20-year-old prospect when they were drafted. And so this is the end result. It's kind of a cool little network diagram that you get. So we're looking at Bo Horvat specifically. Was drafted out of the OHL at 18. The model thinks that he's going to stay in the OHL for an additional season, and then from there it kind of branches out. So each predicted league creates its own unique path, and many of these different paths, we're trying to get to the NHL essentially. Not all paths are equal, and not all paths maximize NHL potential. And so from here we can kind of derive some cool metrics. So in the Apple world, expected value is kind of that expectation conditional on those NHL nodes. So essentially weighted by the probability of you being at that NHL season, what are the sum of your points in totality? From there, we can also look at things like player seasons. Like I said before, not all paths are equal. So this would be the path with the highest cumulative NHL production. So for Horvat here would be that leftmost path. And we could also borrow from some old literature and have something like NHL make percentage. So that would just be the probability that that player plays at least one NHL season in this network graph. Well, we also have the benefit of V2. So V2, like we said before, is more predictive. And we also get a posterior distribution. By that, we have a distribution of projected scoring for each of those seasons. And to me, it's more interpretable. So you take someone like Tim Stützle, for the Ottawa Senators this season, he had only about a 78% chance to play in the NHL based on the model. And his mean expectation was about 0.63 points per game, which is around a top 6 forward. And so far, it seems to have checked out for that player. But you can also see that there was room for him to score more or less. And so for me, this is a lot more interpretable and provides you a little bit more intuition as to what the model is doing in expectation. So how else can we validate Apple? Well, what we can do is we can take a look at the Apple expected value of a draft prospect at the time that they were drafted and see how well it correlates with their actual NHL scoring. And so for forwards and defensemen, the model does really, really well. 0.56 R-squared, 0.45 for defensemen is quite was something that I wasn't expecting, mostly because we're not actually fitting on their actual NHL scoring as the response variable for this model. It's just a metric derived from the components of the model. All right, now onto the kind of retrospective limitations and everything. You always have to talk about your model's shortcomings, and for Apple, it has to be, you have to look at the leagues. If you talk to any prospect writer, scout, analyst, there's been a lot of research done on regions where we have underscouted or overscouted regions. People are talking about the USHL as a place where a lot of good prospects are coming from, as well as the Nordic countries. But you look at Russia, and on this graph on the bottom right, the KHL and MHL have the two lowest expected values for first rounders in our entire sample. And these are kind of the leagues that I chose as being the top leagues to draft from. And this kind of goes against what you would intuitively think. Katarina Wu at CBJ Hack last year had done some research on league strengths, and the KHL always duels with the AHL as being the second best league in the world. And so there has to be something going on here. And for lack of a better term, there's always this Russian bias for a lot of teams and for players, and you don't really know. It's kind of a chicken and the egg problem, because you draft a player from Russia, do they come over? If they don't, do they just stay in Russia? And then that kind of just has like a vicious cycle. And so that kind of comes out in the data. And so we could be undervaluing Russian prospects with something like this. So if you take Kirill Kaprizov, for example, and you foil and you contrast with someone like Evgeny Kuznetsov, at their draft year, they both kind of scored at similar rates. If anything, Kirill Kaprizov outperformed Kuznetsov in age-adjusted points per game. And the only real difference is, Kuznetsov is a little bit bigger, and he was drafted in the first round. But Apple treats them as two different prospects, where Kirill Kaprizov at the time he was drafted didn't look like an NHL prospect in any way. So at this point, you kind of see where the bias might lead you down the wrong path. But I also do think by acknowledging the bias and knowing where it is, you can probably make some tweaks. So one thing that I think that could work is if you have your own internal draft rankings and you're looking at what your edge could be for drafting a player. If you think Kirill Kaprizov in 2015 was a first-round talent, you could impute that value, rerun the model, and see what the delta is, and that would almost be your edge. All right, another thing for retrospectives, is the juice worth the squeeze? I'm not going to lie, this model took a lot of time and effort to even get off the ground, and really to only decreasing marginal gains over something that's been done in the past research, and it makes you think, have you exhausted all avenues when it comes to elite prospects data? There's also things like, who do you give credit to when it comes to development? Do you give it to the team in terms of their development pipeline, their system, their player personnel, or do you give it to the player? So that was something that I was kind of struggling with when I was going through evaluation metrics. And also, I would think that this model could be portable to something like event data. But again, going back to one of the people that I look up to in the sports analytics community, they say that elite prospects data, it's an inch wide but a mile deep, whereas event data, it's a mile wide and an inch deep. So hopefully, as we get more and more event data across time and across leagues, we'll have a better idea if this is portable or not. So really, the main takeaways are that I'm not reinventing the wheel anyway. There's really no difference than just going to elite prospects and sorting by points per game. If you have to score in order for this model, for you to come out good in this model. But I do think the LSTM strikes a balance for model complexity, as we saw the out of sample results were just as good as the in sample results. And I also think that the novelty of this research isn't, or it's in the simulating of the prospect development and not in any one component. So I wouldn't say that the innovation in any way is due to the LSTM. XGBoost, tough customer as the incumbent, really hard to outperform something like XGBoost, and it lends itself to maybe choosing a more interpretable, easy to reproduce model as opposed to writing your own specific neural network. And you obviously live and die by your bias data. Make sure that you know where your model shortcomings are, just so you're not being blindsided. All right, Apple at the draft table. So I borrowed some methodologies from Dr. Shuckers himself, looking at how well Apple and the Apple rankings correlate with draft rankings. It does a pretty good job in terms of predicting the NHL rank here is basically a rank on how many points scored separated by defensemen in their draft +5 season. And yeah, it does better than draft order. But as you can see here, it doesn't do as well as draft by numbers, and probably why I didn't get into Sloan. Draft value chart. It's been done time and again. And we can do it here as well with Apple. And we can do cool things like draft surplus or draft clusters. You can kind of see on the scatter plot here on the forward side that there are, different groups when it comes to draft pick order and the average expected Apple value at that pick. And so that can kind of give you an idea of what draft ranges could be, going back to that kind of simulating the draft spot in the Kirill Kaprizov example. All right, 2021 draft, big grain of salt. I usually love to dive into the prospects, watch video. I am going to admit I did not do any of that for this presentation, but I do know that people like lists. So these are the top 5 forwards and defenders for the 2021 draft. Given that there seems to be a nice little trio of forwards at the top with Kent Johnson, Matthew Beniers, and William Eklund. Pretty high consensus top 5 players in a lot of draft boards, but Owen Power seems to be the head and shoulders best player designated by Apple, and is probably worthy of going to Buffalo. So what does it look like for the website? Well, what's currently available and will continue, and as Michael said, will always be available, are the player cards, the team pipelines, and the historical drafts. I'm working on some new features, as you guys saw with the Tim Stutzel example, these single season projections, as well as the 2021 draft rankings. there are avenues to support the project through Patreon or whatnot, because I do want to have some future development for things like the actual paths that the players take or players who follow similar paths. But again, we're all doing this out of our free time most of the time, and so it's really going to come down to support. So just a summary, we took a look at some of the literature, the framework for this model, model comparison, talking about some of the shortcomings and the biases, draft value for the model, taking a look at the 2021 draft, and I will yield the rest of my time to you folks if you have any questions. If you don't feel comfortable asking questions on the call, you can always reach out to me at these avenues here, and thank you for having me.
Awesome, Connor. Thank you for that. I'm going to give folks a couple of seconds to type in questions in the Q&A. And I appreciate the making that website, the commitment to keeping that website open and publicly available. So that's great. So we've got one in the question here in the Q&A. So what were the most predictive variables of future success other than point production?
Yeah, great question, Ian. So the thing about neural networks is that they're not necessarily the most interpretable models, but I do think when it comes to Apple, the most predictive variable would probably be draft position. If you take a look at something like the 538 Carmela model, they use a combination of stats and scouts, mostly because we have to operate on the assumption that scouts are good, and I believe that myself. So it captures a lot of information that we don't have necessarily access to with something like Elite Prospects. So it's almost just like a proxy for talent.
Yep, good. And I think that's pretty consistent with some of the stuff in the literature. So awesome. Okay, so another question for you in terms of sort of differences and what you've seen, but differences in players developed in Europe compared to North America. Always a question that folks want to answer.
Yeah, I mean, it goes back to one of the initial assumptions of can players move freely from league to league. The model that I chose to predict the future leagues, is a gradient boosted tree. So it really does focus on getting the best prediction. And so for leagues in Europe, it seems as though players can move a lot more free if they're good enough to play in a junior league, if they're good enough to play in a pro league, then they'll play in a pro league. So say, for example, something like Sweden or in Finland, if you're good enough to play in the SHL or Liga, you'll probably play there. Whereas in North America, a lot of CHL prospects are probably too good for that league and have to continue to play in the CHL. And we're seeing the kind of differences now in 2021, where a lot of these CHL prospects who would be in the O or the Dub are actually playing really, really well in the AHL. And so that could definitely change the development curves.
Nice, awesome. Got a couple more here for you. So did you notice any particular teams outperforming or underperforming sort of the expected values for their prospects?
Yeah, and there are a lot of teams or people representing teams on this call. I don't want to disparage anybody in particular, but I will say that people who have done research in the past about teams that have outperformed potentially their draft position, it's about the same. You're looking at Boston, looking at Carolina. I think New Jersey was also up there as well.
Good. I think we've got time for one more quick one. And the question is, how does the model do for defensive defensemen versus offensive defensemen?
Yeah, that's the thing, right? it definitely undervalues the defensive defenseman, mostly because for this model, you need to score in order to get to and graduate to the next league. So, I mean, it's an age-old question. I'll say, you still need, even if your tropes as a player and your strengths as a player is the defensive side of the game, you still need to score in order to, be at evens in the next league that you're trying to jump to. So, I mean, I think that's one that's also done pretty well in the literature. Was there a second part to that question, Michael?
No, I think that was it. It just in terms of is there a way that your model handles those in particular?
No.
Yeah, awesome. Well, thank you again, Connor. Really appreciate it. Nice job, and yeah, happy to see that. So I think I turn it over to Megan.